Well friends, welcome to the fourth part of basic law of thermodynamics. In this, we will try to see Carnot cycle. How do you calculate the COP of Carnot cycle, refrigerator, reversible engines, and finally entropy. In the second law of thermodynamics, we said there is a randomness introduced. That randomness is entropy. We will see that in detail. Carnot cycle is a reversible cycle. It is a ideal hypothetical cycle in which all the processes constituting the cycle are reversible. So, when we draw a PV diagram, we will see A, B, C and D, AB, BC, CD, DA. AB is isothermal, BC is adiabatic, CD is isothermal and DA is adiabatic. So, here there is heat in, here there is heat out, right. So, for a stationary system, as in piston cylinder machine, in piston cylinder machine, you will have a cylinder, you will have a piston. This piston will move up and down. So, here we are attaching it to a lever and then that in turn is attached to a smaller. So, let us make it as a link 1 and a link 2 and then it is attached to a point. So, now when this rotates, it can transfer, it can rotate a shaft or it can transfer energy. For a stationary system, as in a piston and a cylinder machine, the cycle consists of 4 steps. As I told you, isothermal heat addition, isothermal heat rejection, adiabatic expansion and adiabatic compression. 4 cycles happen. The Carnot cycle is a reversible cycle that is composed of 4 reversible processes. So, what happens in isothermal expansion? We are seeing a animation here. I have made it into 4 parts. So, in the adiabatic, in the isothermal expansion, when it moves from 1 to 2, you can see that the piston is trying to expand. It is trying to go up. And when it goes from 2 to 3, it is adiabatic expansion. So, still the piston is expanding. So, then 3 to 4 is isothermal compression which happens from 3 to 4. Isothermal compression happens and from 4 to 1 you can see that adiabatic compression happens. So, when there is a heat which is given, there is an expansion happening and once the expansion is saturated, then the weight is there. This weight is trying to push it down once again. When it is trying to push it down, it is trying to compress. So, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. The 4 processes in a Carnot cycle are 1 to 2 is reversible isothermal heat addition. 2 to 3 is reversible adiabatic expansion. 3 to 4 is reversible isothermal heat rejection. And 4 to 1 is going to be reversible adiabatic compression. If you see the TS diagram, it looks like a simple rectangle. The same thing what we have dealt in the previous slide, add, reject, work E, work C. Work E is work in exhaust or expansion and then here it is of compression, volume change, compression. So, the net Q cycle is equal to net W cycle. So, Q add minus Q reject, Q add minus Q reject is equal to W work exhaust minus work compression. So, if you want to calculate the efficiency, it is going to be work net. So, what is work net? Work net is going to be WE minus WC. Work net is this, and then you will have the heat. So, W net divided by heat add to the system, which is Q add minus Q reject by Q add. So, if you are looking for the efficiency, it is going to be 1 minus Q reject by Q add. When we go from TS diagram, it is going to be 1 minus T2 into delta S is entropy divided by T1 into delta S. So, the efficiency is equal to 1 minus T2 minus T1. So, the Carnot cycle, which gives you little more insight, is the efficiency of an irreversible heat engine is always less than the reversible engine. The efficiency of all reversible heat engines operate between the same reservoirs are the same. Since the efficiency of all reversible heat engines operate between the same heat reservoirs are same, the efficiency of the reversible engine is independent of the nature or the amount of working substance undergoing the cycle. So, please note it down. So, this can be a question which is asked in the examination. The efficiency of a reversible engine is independent of the nature or the amount of working substance undergoing the cycle. Clausius inequality, which is also an important thing which you should understand. The cyclic integral of delta Q by T is always less than or equal to 0. So, it is 0 or less than 0, right? 0 or less than 0. So, if you take positive minus, right. So, mathematically it can be represented as the cyclic integral delta Q by T, which is less than or equal to 0. The equality, this we are talking about inequality, the equality in Clausius inequality holds for totally or just reversible cycles and the inequality for the irreversible cycles. So, this is a reversible engine. T is the temperature, Q1 is the heat. So, which goes to heat engine, which is reversible, Q2 which is after doing work, Q2 it comes, which goes to the sink. Let us look at refrigerator. Refrigerator are also a cyclic device used to transfer heat from a lower temperature medium to a higher temperature medium. The working fluid used in refrigeration cycle is called as refrigerant. So, if you go back and see, we have said that in a Carnot reversible heat engine operating between the same heat reservoirs are same, the efficiency of reversible engine is independent of the nature or state of the work. The most frequently used refrigeration cycle is a vapor compression refrigeration cycle. We will see this vapor compression refrigeration cycle later. COP is an important terminology which is used, coefficient of performance. The coefficient of performance for a refrigerator is always defined as desired output by required input. Desired output will be Q2, required input will be work. So, COP for a refrigerator will be Q2 by Q1 minus Q2. So, what we are trying to say is the high heat reservoir surrounding is there. So, from a cold you apply 2 and then you put a work. So, that gets converted into 1 and then you start doing the throwing of air inside. Also, COP-HP for a heat pump is equal to COP-R plus 1. So, this is important. COP-HP heat pump is equal to COP-R plus 1. Okay. So, this is very important, coefficient of performance. The refrigerator is a heat pump device that operates on the principle of transferring heat from a lower temperature region to a higher temperature region, from a lower to a higher temperature region. Unlike heat engines, which converts heat into work. A refrigerator consumes work to remove heat from the space that must be kept cool and reject it to the warmer surrounding environment. So, this is expansion valve. We have seen this in the previous lecture itself. You have a compressor where pressure temperature increases, then you have an evaporator. So, then from the evaporator it goes to the refrigerator sink or space. Then from there you can see that expansion happens and then it goes to condenser. So, you can try to take in this way: condenser to the expansion valve to the evaporator, evaporator to the compressor, and then this gets. So, once the air is compressed, it moves to a compressor. Right? From a compressor, it tries to expand. Why does it do? Because it has to take heat and then it has to give the cold air. This process seemingly goes against the natural flow of heat, which is because from a hot body to a cold body it goes. Now, you are moving to move a cold body to a hot body. So, which is from hot to cold and is only made possible by doing external work as explained by the second law of thermodynamics. So, a refrigerator works and this is how it is. So, typical refrigerator works on vapor compression. So, you use vapor and you compress in a refrigeration cycle. Compressor, it compresses the refrigerant gas, raising its pressure and temperature. Compressor compresses the refrigerant gas. When it compresses, the pressure increases, temperature increases. So, then that leads to vapor which comes here. The condenser, the high pressure hot gas flows through a condenser coil where it loses heat to the surrounding and condenses into a high pressure liquid. So, high pressure hot gas flows through the condenser coil where it loses heat to the surrounding and condenses into a high pressure liquid. So, temperature goes, high pressure liquid. So, the expansion and capillary tube, the high pressure which comes out liquid refrigerant passes through this valve and it reduces the pressure. Expansion means it's reducing the pressure rapidly and causes a partial evaporation. This partial evaporation, whatever is there, the low pressure liquid absorbs heat from the inside of the refrigerator and evaporator, cooling the space. The cycle then repeats. Right? So, compressor, condenser, the expansion valve, capillary tube and evaporator. There are 4 things which are there in a refrigerator. It follows a vapor condenser. Vapor is solid, liquid, gas. Vapor comes in this phase, solid, liquid, vapor phase. Right? So, we also saw the latent vapor in the beginning lectures. We saw that fundamentals. So, here it is very simple. Compressor, which there is a liquid or a gas, compressor gas. So, it is compressed. So, when the gas is compressed, pressure and temperature goes high. Once it is compressed, what happens? It can't be kept on compressing. Then it condenses. The high pressure hot gas flows through a condenser coil where heat is lost, because the vapor, the heat is lost to the surrounding and condenses into a high pressure liquid. Vapor which was there gets converted into a liquid. Now, that liquid refrigerant passes through a valve which reduces its pressure rapidly and causes partial evaporation. So, the evaporator, the low pressure liquid absorbs heat from the inside of the refrigerator and evaporator, cooling the space. The cycle then repeats. Right? So, these are all little examples or which talks about the refrigerator, because as a engineer you should understand how does the refrigerator work. So, the refrigerator is widely used in home appliance, where all it is used we have said here. This ability to maintain low pressure between preserve foods, extend shelf life, prevent microbial growth and maintain all these things. So, what is happening? You try to take the heat out and you give the cold. In modern systems, eco-friendly refrigerants are used. CO2 is also used, right, which reduces the environmental impact. The efficiency improvement in the refrigeration technology are crucial for energy conversion. Engineers aim to minimize power consumption, reduce irreversibility, aim to minimize power consumption, reduce irreversibility, and improve the reliability and sustainability of the refrigerant cycle. So, this is what is our goal. I repeat, engineers aim to minimize power consumption, then it reduces irreversibility and improve the reliability and sustainability of the machine. Okay. So, this is refrigerator. So, in a crude sense, refrigerator is different from heat engines. Unlike heat engines, which converts heat into work, a refrigerator consumes work to remove heat from the space that must be kept cold and rejected to the warmer surrounding environment. The last topic in the second law of thermodynamics is entropy. The property of entropy was introduced through the historical route as initiated by an engineer Carnot and elaborated by a physicist Kelvin and Clausius. Starting with the statement expressing the impossibility of converting a heat completely into work or impossibility of spontaneous heat flow from a colder to a hotter body, an ideal heat engine of maximum efficiency was described. With the aid of its ideal engine, an absolute temperature scale was defined and Clausius theorem proved it. On the basis of Clausius theorem, the existence of entropy function was inferred. The entropy is a measure of randomness or disorder of a system. So, this is low entropy material will be, this will be high entropy material will be. The entropy increases as and when you apply energy to it. Entropy is a central concept in the second law of thermodynamics and serves as a quantitative measure of disorder, randomness, and energy unavailability in a system. In simple terms, entropy indicates the degree of spreading or dispersal of energy. It indicates the degree of spreading and dispersal of energy. When energy is transformed, such as heat flowing from a hot body to a cold one, not all of it remains available to be useful work. And this loss is reflected by a increase in entropy. So, when does or how does an entropy increase? Is entropy indicates the degree of spreading or dispersal of energy. When the energy is transformed such that the heat flowing from a hot body to a colder one, not all of its remaining available to be useful work. In the reversible process, the total entropy change of a system and the surrounding is 0 in the reversible, but whereas in irreversible process, the total entropy always increases. S increases when it is irreversible. So, this is low entropy. When the temperature is applied, there is a high entropy. Entropy generation refers to irreversible increase in entropy during a real-time thermodynamics. In a direct measurement of loss of useful energy and indicate inefficiency within a system is increase in entropy. According to the second law of thermodynamics, entropy generation occurs whenever there is irreversibility such as friction, unrestrained expansion, heat transfer across a finite temperature difference, chemical reaction, mixing of different substances, electrical substances or more. In ideal process, entropy remains constant for the system and surrounding. In ideal process, the entropy remains constant for a system and surrounding. But in real world, the total entropy of the universe increases, which includes system plus its environment. So, if you want to mathematically express entropy, it is entropy delta S total is equal to delta S system plus delta S surrounding, which is equal to S gen, which is greater than equal to 0. So, if the S gen is entropy generation, if S gen is greater than 0 for a real process, if generation is equal to 0, it is an ideal process. If it is less than 0, it is a impossible or a violation of second law. This is the entropy. So, the entropy generation is essential for understanding. Irreversibility in the real process will be found out by entropy. Limit of the performance is also there. Waste energy and where it occurs is also known when we try to study the entropy. Design improvement by pinpointing inefficiency is done when we try to understand the entropy concept. Environmental impact as high entropy generation often corresponding to a higher fuel consumption and emission is also there. Entropy generation acts as a thermodynamic cost of performing any process in real world. But minimizing it, we approach the ideal reversible process and attain maximum efficiency. The thermodynamic system TDS relationship. So, the entropy is a measure of disorder of a system. The entropy increases for a solid, then for a liquid, then for a gas. So, when you melt it, from melting goes on solid to liquid, and when you try to apply more heat, vaporization happens. Vaporization to liquid, it is condensation. So, if you can go back to your vapor cycle, which is used in refrigerator, right, vapor compression. So, it is vapor, compression comes into liquid, then liquid freeze, it becomes solid. Okay, this is a cycle. So, here you can see the how the entropy increases. So, delta Q reversible is equal to the thermodynamic stability, but delta Q rev is nothing but thermodynamic TDS, and delta W rev is nothing but PVD, work is nothing but PdV, delta P. So, thus the first TDS equation is obtained as TDS is equal to du plus PdV. The second thermodynamic system equation is obtained by using the definition of H equal to U plus PV. So, delta H is equal to delta U plus delta PV, which is du plus PdV plus VdP. When you try to rearrange all those things, you try to get on a unit mass basis is TDS is equal to du plus PdV, TDS is equal to dH minus VdP. So, the entropy change in an ideal gas, the entropy change between two states of an ideal gas can be obtained from the ideal gas equation and combined equation of the first and second law. TDS is equal to du plus PdV. S2 minus S1 is nothing but constant volume, natural logarithm of T2 minus T1. Du is equal to Cv dt and P is equal to RT by V. Therefore, when we try to do TDS, it is du, you put this here, and PdV, you put this here. So, when we try to integrate this ds, Cv dt and this thing, we try to get S2 minus S1, which is Cv natural logarithm of T2 by T1 plus R times natural logarithm of V2 by V1. So, which is again TDS is equal to delta H minus VdP. Delta H is equal to Cp into dt and V. So, the RT by V is given like this. So, then you go back and substitute it back into the equation. So, you get TDS. So, this is H. So, you get this. Then TDS, you try to bring the T on both sides, and then you try to integrate it. So, we try to have Cp dV dt minus R times this, and finally, S2 minus S1, which is represented in this form, Cp natural logarithm of this. So, we are trying to find out the entropy change in an ideal gas from the base equation. So, S2 minus S1, we are trying to write it as Cv into this, du is equal to Cv into this, P is equal to this. So, TdS is this which happens, and then this is what it is. So, the application of entropy, where all do we use? So, the principle of increase in entropy is one of the most important law of physical sciences. It has the equal quantitative statement of the second law of thermodynamics is the application of entropy. Even irreversible process is accomplished by a entropy increase of the universe. The higher the entropy increase of the universe, higher is the irreversibility of the process. Higher is the entropy increase, is the higher the entropy principle helps engineer to find out the possibility of a process, the efficiency and the loss of a process, guide for sustainability system. So, these are the principles where entropy is used for an engineer. The entropy can be transferred to or from a system in two forms. Either it transfers heat or it transfers mass. So, heat transfer and mass flow can happen in the entropy. In contrast, the energy is transferred by work, but entropy is transferred by two forms, heat transfer and mass flow. In energy, it is transferred as only work. The entropy transfer is recognized as a system boundary as entropy crosses the boundary, and it represents the entropy gained or lost by the system during the process. This statement is also very important. Entropy transfer is recognized at the system boundary as entropy crosses the boundary, and it represents the entropy gained or lost by the system during the process. The only form of entropy interaction associated with a fixed mass or closed system is heat transfer, and thus the entropy transfer for an adiabatic closed system is 0. Important. The only form of entropy interaction associated with its fixed mass or closed system is heat transfer. When it goes to adiabatic of an adiabatic closed system is 0. So, low entropy, low disorder. This is high entropy and high disorder. It is important to note that one is interested only in the amount of the entropy of the system changes is going from initial to final and not its value. In case where it is necessary, a 0 value of entropy of a system at an arbitrarily chosen standard state is assigned, and the entropy changes are calculated with the reference to that standard state. So, this is also important. These two are very important. In case where it is necessary, a 0 value of entropy of a system at an arbitrarily chosen standard state is assigned, and entropy changes are calculated with reference to its standard state. So, here we will try to have all those things. This is what it is. So, the increase in temperature, what happens to the things. So, you can see this very clearly, what happens to temperature, what happens to work, what happens to entropy. Friends, in this chapter, we saw what is heat engine, what are its various types, state and describe the component of heat engine. Then we looked into Carnot cycle and its working. We understood reversible engine. Then how does a refrigerator work and how is it different from heat engine? What is a heat pump? How does it work? And finally, we understood entropy and its importance along with its applications. These are the references, and thank you very much.